Now we're going to look at how we can use graphs to be able to determine the rate law. All right, so we can take concentration versus time graphs and determine the rate law by looking for a straight line here. So graphs will be different for zero, first, and second order. We will put time on the x-axis and then concentration on the y-axis in these graphs. And basically, we're looking for a straight line. If you plot the data in a certain way and you get a straight line, that can tell you whether it's zero, first, or second order. And that's what we're going to look at here in this video, how we can use graphs to determine the rate law. For a zero order reaction or a zero order reactant, if you take concentration versus time data, graph them, and you get a straight line, then you know that you have a zero order reaction or a zero order reactant. K will have a negative slope. If you look at the picture here, you can see when you plot the data, right, the slope would be negative, but K itself is never negative. All right, so just be careful though. In the rate law itself, K is not negative. It just has a negative slope here when you plot the concentration versus time. Again, you plot concentration versus time and you get a straight line. That's what's telling you here that it's going to be zero order for that reactant or that reaction. So if you wrote the equation of the line here, y equals mx plus b, essentially on the y-axis, you would have your concentration at a particular time equal to negative K. Remember, K itself is not negative. It's just that the slope is negative here, times time, plus the concentration here at time zero. B would be the concentration at time zero. So your y-intercept essentially is the concentration at time zero. So all we did here was write the equation of the line, but we used information from the graph here. So A T, concentration of A at time T, you get from the graph here. We have K being the rate constant, T being the time. We do got to watch our units here, make sure that they cancel out with K. And then A sub zero is the concentration of A at time zero, or your y-intercept here. All right. The AP equation sheet does not give you this equation, but they will give you the other two equations. So that makes me think that they're not going to make you use this equation necessarily on the exam, or they expect that you'd be able to figure it out by looking at the other two. So just be aware of that. But anytime you do concentration versus time data and you get a straight line, you know that the reaction or that reactant is going to be zero order. And then you can even use the equation of the line to maybe figure stuff out here, as you'll see. If we plot the natural log of the concentration, so the ln of the concentration versus time, and we get a straight line, then we know the reaction or that reactant is going to be first order. So if you look at this graph here, you can see we plotted the natural log of the concentration versus time, and we got a straight line. That tells us this is first order here. K is going to have a negative slope again, even though K itself is never negative in the rate law. So we can write the equation of this line again, y equals mx plus b, but this time we're using the natural log of the concentration. So y would be your natural log of the concentration at a particular time equal to negative kt plus the natural log of the concentration at time zero here. To do the natural log of the concentration, you do have to use the ln button on the calculator. AP does give you this equation. The only difference is on the equation sheet, what they do is they subtract the natural log of A at time zero from both sides. So essentially, they just have it listed as the natural log of the concentration at a particular time minus the natural log of A at time zero is equal to negative KT. All right, so it's the same equation. They just kind of have the natural log at time zero subtracted from both sides, and on the left side here, but it's exactly the same thing, and you can use that equation, you get the same answers here. All right, so you should be aware of this equation. You definitely need to realize that a natural log of the concentration versus time graph giving a straight line means first order here. You never know what you could be expected to do here. Sometimes, a problem might tell you it's first order and you have to like label the axes. Sometimes you have to look at the graphs and see like, oh, the natural log versus concentration graph is the one that gave the straight line. So that means it's first order. So you definitely need to be aware of all this information and definitely be able to use the equation to solve problems here, as we will see. If you plot 1 over the concentration versus time and you get a straight line, that indicates here that a reaction or a reactant is second order. Okay, so this time we're doing 1 over the concentration versus time, giving us a straight line. This time we get a positive slope, and you should be familiar with that. You should understand here that if you're getting, a straight line for 0 or first order, it's going to have a negative slope, and if you're getting a straight line for second order, it's going to have a positive slope. You could be asked to draw what the line would look like, so you definitely need to be aware of that. So we're going to use y equals mx plus b here again to get the equation of the line. It's just 1 over the concentration at a particular time now equal to kt. Notice it's positive slope now, plus 1 over the concentration at time 0, which would be your y-intercept. This equation is given on the equation sheet as well, but again, they subtract the 1 over the concentration at time 0 from both sides, and that's the way they give it to you, but it's still the same equation here. Again, you need to be familiar and understand that 1 over the concentration versus time plotted and giving a straight line is going to be a second order reaction or a second order reactant, and be able to use the equation here to do some math with this. All right, so definitely be able to understand what you're plotting for each of the orders, and knowing that a straight line for one of those gives you or tells you that you have a particular order, or gives the particular order for a reaction or a reactant. Let's look at an example now of how you can use those equations of the line to determine something here with concentration or time. It says in a first order reaction, and now that's important. They're telling you right away this is a first order reaction. A common insecticide breaks down into various products. The rate constant is 1.45 years to the -1 at 12 degrees Celsius. If the concentration of the insecticide is 5.0 times 10 to the -7 grams per centimeters cubed, we want to know the concentration 1 year later, and, so a second part here, how long it will take to change the concentration to 3.0 times 10 to the -7 grams per centimeters cubed. So the first thing we need to do is we need to realize, okay, this is a first order reaction. I need to use the first order equation of the line. All right, in your head, you should be saying, okay, if it's first order, a natural log of the concentration versus time would give me a straight line. So I need to use the natural log of the concentration equation here. All right, so you have the natural log of the concentration at a particular time equal to negative kT plus the natural log of the concentration at time 0. Again, a version of this is given on the equation sheet. They don't tell you that it's first order. You have to know that this is the first order equation. So we are trying to find, the first thing is we're trying to find the concentration 1 year later. So we are trying to find the concentration at a particular time, 1 year later. We're not trying to find the concentration initially. All right, so you're not looking for this. You're looking for the concentration here at a particular time. So if we plug in, we'll plug in what we know. So we're solving for the natural log of the concentration at a particular time. They told us what K was. All right, they gave us the rate constant. We plug it in. You do need to watch your units here. When we get to T, that's time. Well, they're telling us it's 1 year later. Our units do match, so make sure of that. Years to the -1 and years would cancel here. So that's what we want. And then we're going to add this to the natural log of the concentration at time 0. They told us the initial concentration of the insecticide here. So now it just becomes math and being careful. All right, so if you solve kind of this part of the equation here, I would do the natural log of the 5.0 times 10 to the -7, hit equals, add that to your -1.45 times 1, and you would get to this point. Make sure you can actually do the math on your calculator to get to this point. So now you have the natural log of the concentration at a particular time equal to the -15.96. Your calculator might have given you a longer number. You can use, and probably should use, the entire number here. So you're trying to solve for the concentration at a particular time, all right? but you have this natural log there. The way to get rid of it on your calculator is you do what I like to call, I don't know if this is the right wording, but I call it the inverse natural log. So you do second ln button on your calculator, second ln button, and that'll get you e to the power of. And then if you put in this answer you got here, I like to use the answer button on the calculator because it will remember it. And you hit equals, you'll get the concentration at a particular time here. So be careful with that. To solve this for the concentration at a particular time, to get rid of the ln, you do second ln button, which gives you e to the power of, put in this answer, hit equals, and then you get the concentration at a particular time. You do have to sig fig it and watch your units here, but it should come out to be 1.2 times 10 to the minus 7 grams per centimeters cubed. So one of these problems is really that simple. Pay attention to which equation of the line you need to use based on the order of the reaction, and pay attention to what you're solving for and watch your math. And always, be careful of your units in the problems. Now we want to do the second part of this equation, and I have it shown here for you so you can kind of follow along. We want to know how long it will take to change the concentration to 3.0 times 10 to the minus 7th grams per centimeters cubed. So again, first order reaction. So we have to use the first order equation here. You should be saying, okay, first order is the natural log of the concentration versus time, giving a straight line. So I need to use the natural log version of the equation here. This time, we're solving for the time, how long it will take. All right, so our concentration at a particular time is going to be the 3.0 times 10 to the minus 7th grams per centimeters cubed. All right, so that's what we're plugging in here, ln of that. Equals negative k, which we know k already is the rate constant from the problem, times time, which is what we're solving for, plus the natural log here at time 0, which we already know is the 5.0 times 10 to the minus 7. So it's the same idea as last problem. The only difference is you're solving for the time in this one. And realize here, when you do solve for time, your units are going to be years here based on your rate constant. So pay attention to that. If you need to have a different unit, you might have to convert. Just watch that. So now it's just, doing the math here and solving. I would obviously do the natural log here of this, subtract the natural log of this from both sides. And when you do that here, so I kind of did that all in this step. Here's the natural log of this. Obviously, you should give the whole number. Here's the natural log of this. When you add this now, essentially, to both sides, you get negative 0.51 equals the negative 1.45 t. Divide both sides by the negative 1.45. Solve for t. Watch your sig figs and realize your units are going to be based on the rate constant. So it would take about 0.35 years in order to get the concentration to this point. All right, so again, pay attention to the order, use the correct equation, plug in, solve, and watch your units and sig figs. I just want you to see this example real quick so you would know how to go about solving it. This one says, use the data given to determine if the following reaction is first or second order. And they gave you the reaction, they gave you time, they gave you concentration data here at those times. So the quickest way to do this was you would just have to plot the graphs, all right? You already know that it's not going to be zero order because they're not asking that. That would be a concentration versus time graph. But essentially here, you would have to do the natural log of all the concentrations, get all those numbers, and then plot natural log of the concentration versus time data and see if you got a straight line. And you can do 1 over all the concentrations, get all that data, plot 1 over the concentration versus time, see if you get a straight line to see if it's second order here. And when you do plot this, the graph that ends up being straight is the second order graph, the 1 over concentration versus time graph. So this reaction must be second order. There's only one reactant, so it would be rate equals K times the concentration of NO2 squared here. Okay, so I just want you to be aware of this. I never thought you would see something like this on an exam, but I did see a question where you kind of had to quickly plot a few points in order to determine which graph was straight here. Obviously, you could be expected to take lab data and need to plot it 3 different ways and find the straight graph in order to determine the order. And I never thought you'd see this on an exam, but I have seen a question where you had to use graphs to do it. So you actually had to plot the data very roughly and real quick to determine the order of the reaction. So just be aware of this. Obviously, you're looking for the plot that gives the straight line to determine the order. Let's look at another example here. This one says, use the data given to determine the concentration of CH3 CBr after 2 minutes. The reaction is first order, right? So that's important. The reaction is first order here, and the rate constant is given. So you can see the reaction. They gave us time and concentration data, but we already know the reaction is first order here. So we should know, okay, first order, when you plot the natural log of the concentration versus time, you're going to get a straight line. So you need to use the natural log of the concentration equation here to figure this out. First thing you want to realize here, the rate constant is in seconds to the -1. The time is 2 minutes. So your units need to match here. So you're going to need to convert. I'm opting to convert to time. So if I take 2 minutes here, all right, we know that there's 60 seconds for every 1 minute. So our time here, when our minutes cancel, will be 120 seconds. We have to have our units of time and the rate constant matching so they cancel. So we already said we know we're using the natural log version of the equation. Natural log of the concentration at a particular time is going to be equal to negative KT plus natural log of the concentration at time 0 here. All right, so in this problem, we're trying to find the concentration after 2 minutes. So we're trying to find the concentration at a particular time. So we're solving for this right there. So when we plug everything in, natural log of the concentration at a particular time is what I'm looking for, equal to negative K. They told us the rate constant here was 9.9 times 10 to the -3 seconds to the -1 times the time, which we said we converted here is 120 seconds, plus natural log of the concentration at time 0. So we have to look that up. They didn't tell us that. We have to look it up here on the actual chart. So we know we're going to do natural log of 0.100 molar. Okay, so now you're just going to do the math here and solve. I'll show you kind of my intermediate step. When I did the math on the right side, I got the natural log concentration at a particular time equal to negative 3.490585093. All right, so again, I want to solve for the concentration at a particular time here. So I would do the second ln button on your calculator, put this answer in, this negative 3.49, hit equals, and then when you get the concentration here at that particular time, with correct sig figs in units, should be 3.0 times 10 to the -2 molar. Obviously, you could use 0.030 molar as well. Either of those works. You have your 2 sig figs and you have molar as your units. All right, so this was just another example. Watch your units of time with your K units here, but do the math correctly, plug in, and solve. Now we want to look at this idea called half-life. Half-life is the time required for the concentration of a reactant to reach half of its initial value. So if you have a starting value for a reactant, how long does it take to get half of that starting value, essentially? In a first order reaction, the concentration of the reactant decreases in half by regularly spaced intervals. That's very important here. Understanding that for first order reactions, this happens in regularly spaced intervals. You might have to answer questions about why you can determine the half-life here for a particular reactant or reaction, and understanding the idea that, oh, this works for first order reactions or first order reactants because the concentration decreases in half by these regularly spaced intervals. It can be very useful for radioactive decay calculations, right? If you know how long here it takes, what the original concentration was, and then the now concentration, you can see how many half-lives something has gone through to be able to determine about how long ago something was living. So it's actually very useful here. So half-life is the amount of time it takes to get half of its original concentration. This picture gives you a little bit of an idea about how this idea of radioactive decay calculations works. So if you notice here, we have this corn plant absorbing carbon during photosynthesis, and then eventually a turkey comes along here and consumes that carbon when it eats the corn. The carbon is absorbed into all the tissues and the bones of the turkey itself. Then eventually this turkey is killed and one of its legs is turned into a weapon here. All right. So what happens here is as soon as that turkey is dead, the carbon that was in the bones starts to decay at a known rate. And it's releasing this radioactive carbon, carbon 14. It's just an isotope of carbon from all of its tissues, including the weapon here, including the bone. So what happens is that gets lost, gets buried, and then many, many, many years later, maybe even millions of years later, um, we find this bone, okay, and it's dug up, and then they can measure how much carbon 14 is left in the bone. And because we know the rate here of decay, we know the half-life here, and it's decaying at a certain rate, we can determine roughly how long ago it was when that turkey died. All right, so this is this idea of half-life and being able to realize here that the concentration drops by half here in a specific interval of time. So now we have this equation we can use for half-life here. T to the 1/2 stands for half-life, and that's equal to 0.693 all over K, the rate constant. So this equation is on the equation sheet. You just have to know how to use it and when to use it. But remember here, this works for first order reactions because there's regular intervals here that we see for the half-life. All right. So if you notice here, these two little tables are just showing you at time 0, you'd have 100% of the sample. Well, when one half-life has passed, you would now have 50% of your original sample. All right. When the second half-life comes along, however many years or time that is, it could be seconds, it could be years, whatever. You now have 25% of your original sample. So essentially 75% was gone. And if you have another half-life taking place, you'd have half of that, which is now another 12.5% remaining. So you can see here, it just keeps dropping by half each time. So realize it should never reach 0 here based on math, okay? So if we look at this now in terms of actual amounts and times here, if initially you have 0, you're at time 0, your sample has a mass of 120 grams. Well, 3 years go by, and now your sample is half gone. So the half-life here would be 3 years for this particular substance. So that means then in 6 years, you have half again. So 60 now halves to 30. And then in 9 years, you'd be half again. This has to 15, and so on. All right. So this is this idea of half-life. And just realize here that this occurs over regularly spaced time intervals for first order reactions. In this particular example, you're actually given a graph, given data, and you could be expected to have to do something like this. And it wants to know what is the half-life of the sample below. All right, so if you look at this here, we can see that at time 0, we have it says counts per second of being 80. All right. So if I'm trying to figure out the half-life, if I can see how long it takes to get to half of that or 40, I can figure out the half-life here. Well, if you notice, it took 2 days to get to 40. All right. So half of 40 then would be 20. Let's just confirm that our half-life really is 2 days here. So half of 40 is 20. Does it take another 2 days to get to 20? Well, if you notice, to get to 20, now you're at 4 days. So that would be another 2 days. So it looks like the half-life here is 2 days. Now, because it's occurring over this regularly spaced interval, and you could keep checking it to see if it continues, because it's happening over this regularly spaced interval, you could say that this is a first order reaction or first order reactant here. But that's how you could use a graph here just using the idea of, hey, if I have this much to start with, how much time does it take to get to half of that amount? And you can even confirm that it does apply over the entire sample here. So let's look at this example. It says use the data from the first order reaction below. We're going to find the value of K and then the concentration of A when 20 minutes have passed, and we're going to determine the half-life here. So let's work on part A first, determine the value of K. What some people want to do is they want to kind of look at the data right away and see if they can determine the half-life here. So if you notice, we're starting at 2 molar, and what some people say was, oh, well, if I just figure out, what will the time be to get to 1 molar, I could figure out the half-life. Well, you don't know if it's going to continue kind of decaying here at that amount. We don't have actually half the amount even shown in the table. So you have to be careful here. You're going to have to use your equations of the line here for first order, knowing that natural log of the concentration versus time would give a straight line, and we're going to have to use that to determine the value of K. So just be careful here. Just because you see half-life, don't try to just figure out what the half-life is from the data by guessing, because you don't know if it's going to decay and keep dropping the concentration like that. It could change after 10 minutes. It could start being a little different. We don't even have a complete half-life here, essentially. So we're going to use this natural log of the concentration at a particular time, all right, equal to negative KT plus natural log of the concentration at time 0. And we're going to solve for K. That's going to be the rate constant here. So if we plug in here, I picked one of the data sets from the table. I picked, I didn't want to use the time 0 because I didn't want my K term to cancel out, essentially. So I picked the one where time wasn't 0. So I'm going to have the natural log here of 1.6 equal to negative K, which is what I am solving for, times time, which would be 5 minutes, plus natural log of the concentration at time 0. So if you notice, at time 0, the concentration was 2.0 molar here. All right, so all I'm doing is solving for K, realizing here that your units for K are going to be based off of the units for the time, but realize you'd be dividing the time by both sides. So your units for K here are going to be minutes to the negative 1. When you solve this for K, make sure you can actually do the math. Don't just assume that you know how to do it. Plug it in the calculator. Make sure you get this with correct sig figs. It should be 0.045, and again, minutes to the negative 1 here. Remember, that's the only way your time units would cancel out here, is if you had K units being minutes to the negative 1. Watch your units of K. All right, so that takes care of part A here. Now let's look at part B. We want to find the concentration of A when 20 minutes have passed. Again, we know this is a first order reaction. So we have natural log of A at a particular time is equal to negative KT plus natural log of the concentration initially here. This time we are solving for the concentration at a particular time when 20 minutes have passed. So we're solving here for the natural log of the concentration at a particular time equal to negative K. We just found K, so it's going to be 0.045 minutes to the negative 1. All right, times time, which is 20 minutes. The units match, so that's good. Plus here, the natural log at time 0, which is going to be 2.0 again. All right, so again, you just got to be careful with your math here. I'll show you what I got here as my intermediate step. Natural log of the concentration at a particular time is equal to negative 0.206852 819. So you'd have to do the second ln times that answer, hit equals, and then you should get the concentration here at this particular time with correct sig figs and units should be 0.81 molar. This is a concentration, so your units need to be molar here. All right, so that takes care of part B. We now have to take care of part C. Part C wants us to determine the half-life. Now we can use that half-life equation because we know the value of K from part A. So remember, write your equations here that you're using. T to the 1/2, the half-life, is equal to 0.693 all over K. So when we plug this in, we get 0.693 all over 0.045 minutes to the -1. Your units here for the half-life are going to be based on K. So if you notice here when you do the math, your units are going to end up coming out to be minutes. So be very careful with that. So when we plug and chug this, all right, the T to the 1/2 here does come out to be 15.4 minutes. If you do your proper sig figs, it's not as exact, but it does come out to be 15 minutes for the half-life. All right, so this is just showing you how you kind of would have to go through an entire problem, maybe use those equations of the line, and then use the half-life equation to find the half-life. I want to look at one more example here, and I want to show you something specific in this example. I'm actually going to show you a slightly different way to do it. So this example says we have a certain first order reaction having a half-life of 20 minutes. We want to calculate the rate constant for this reaction and the amount of time it takes for the reaction to be 75% complete here. Okay, so you could just take the fact that you know the half-life now, plug it into the T to the 1/2 equals 0.693 all over K, solve for K to determine the rate constant here. All right, you could do that, but I just want to show you a slightly different way to do this based on something you might have to do in different problems. Sometimes you can't really work around this. So I'm showing you this logic for future percent problems here. Okay, so first thing we want to do is this is saying that the reaction is 75% complete. All right, so you need to be careful with this. What that's actually telling us is essentially if we started either at a whole 1 or 100, basically what we're seeing here is if we started at 1.0 or even 100 and you have one half-life taking place, all right, that would take you down to 0.5. All right, but that would take 20 minutes. Okay. Well, then if you had another half-life taking place, you'd be now at 0.25, or if you started at 100, 25, and then that would take another 20 minutes, which would be a total of 40 minutes here. All right. You need to realize that once you reach 0.25 here, the reaction is now 75% complete. Essentially, 75% of your original starting value is gone. Okay, so it only takes 2 half-lives in order for this to take place. So just by using logic here, I was able to figure out the amount of time it takes for the reaction to be 75% complete. But I want to show you how you can use this idea to calculate the rate constant. We know it's first order. So if we look at the equation here, we know we have to use the natural log equation because it's first order. Natural log of the concentration at a particular time equal to negative kT plus natural log of the concentration at time 0. We're trying to solve for K. So let's plug in here. The natural log of the concentration at a particular time. So what is our concentration when the reaction is 75% complete? Okay, be careful here. Your concentration essentially is going to be 0.25. All right. A lot of times what people do is they would plug in the 75 or the 0.75 here, but no, at the time when you're 75% complete, your concentration, as you see it from up here, is only 0.25 remaining. All right, or 25% left over. So be very careful of this. You may have to kind of use this idea, use this logic here in problems. Right, so it's something to watch out for. Again, we could have done this a lot simpler, but I want you to show you here how to do the problem using this understanding, using this logic and the percent complete. So this would be equal to negative K, which is what I'm solving for. The time we said was 40 minutes. We already figured that out. All right, plus natural log of the concentration at time 0. We said, because they didn't give us a value here, we were starting at 1.0, or if we had used 100, so it would be the natural log of 1.00. All right, so all you're going to do here is solve for K. When you do that, you get K equal to 0.0346, and it's minutes to the -1 if you follow your units correctly here. So we do want correct units. And then remember, that takes care of K. The follow-up question is, well, okay, what's the amount of time the reaction takes to be 75% complete? We already said that would be 40 minutes. All right. So again, you could have just plugged into the Half-Life equation and solved for K. You would get the exact same answer, but I wanted to show you a slightly different way to do this in case you ever have to use this idea of this percent complete to be able to do a problem. Realize here that your concentration at a particular time is not the percent complete. It's the percent that you actually have left over. All right. So just have a good idea about how to use these equations, use the graphs, use the half-life to be able to determine the orders and information here about the rate.